Now, hope you guys are having a good start to your day. Hope that if you had the opportunity to and wanted to, you went to the 125th anniversary celebration that was at the football stadium last night. Um, Pretty neat that that was organized. So I hope that you did if you wanted to. If you had no interest in that, I hope that you did not have to go. We are continuing to talk about enzymes today, and we're going to add a little bit from where we were the other day. If you remember the other day, we were talking about how, we had one last top hat question that was about specific amino acids being involved in enzymes. We're going to go ahead and rehash a little bit of that, and then we're going to go on to bigger and better, more exciting things today. So we're talking about catalytic mechanisms. So basically, how do electrons get pushed around? And man, there are three major types of catalytic mechanisms. There's an acid-base mechanism, covalent catalysis, and last but not least, metal ion catalysis. Now, there are some more, but those are your big, kind of think about those as the big umbrella topics. Those are the big ones that, most everything that we talk about is going to fall into one of those categories, and some things will fall into multiple of those categories. So acid-base catalysis, movement of protons. That's essentially all that there is to it. Now, there is something known as general acid catalysis, and there's also something, as you might imagine, known as general base catalysis. And the question of this is, or whenever you're dissecting and comparing general acid catalysis to general base catalysis, essentially what you're looking for is you're looking to answer the question, where is the proton? Okay, so in general acid catalysis, we have a general acid donating a proton to a substrate. Okay, so I would say maybe not 9 times out of 10, but quite frequently, this is an amino acid on the enzyme. So I'm going to get my annotate tool out. So, um, so an AA on the enzyme. And think about it as that amino acid is protonated and therefore can donate that proton. So a good example of an amino acid that can be protonated, and actually go ahead and add to the chat, go with a single letter code for an amino acid that can be protonated. So it can have a proton that it can donate to something else. So it has a proton. There's 5 pretty good ones that I can think of right off the top. Single letter code for an amino acid that can be protonated. Perfect. Aspartic acid. Great job, Milo. Thank you very much. So aspartic acid, single letter code would be D, glutamic acid, E. Now, as a follow-up to that, well, the enzyme active site is going to be the protonated residue. So it's not just some random residue somewhere else, it's an active site residue. So where the action is going to happen, the substrate binds, and then uh, right next to that is basically where the chemistry is going to take place. Now, general base catalysis is where a general base accepts a proton from a substrate. And you have an enzyme active site residue that must be protonated. Then last but not least, there's something known as concerted acid-base catalysis. A general acid and a general base must both participate in the reaction. Okay. Now, I'm going to jump ahead because I want to show you an example of this before we, kind of before we maybe get mired in some of the details. Okay, so I want to introduce these to this right here. This is a um, this right here is a catalytic mechanism. And there are a couple of things that I want to draw your attention to. And I think that it's going to be helpful anytime you see an enzyme catalyzed mechanism in the future. We've got this kind of 3/4 circle or this semicircle that's kind of a brownish color. Think about this as our enzyme, basically our polypeptide, our 350 amino acids that make up this enzyme known as ribonuclease A. Now, does this image show all 300 or 100 or 190 amino acids or 139? No, it doesn't. We've got two that are highlighted. Where do you think those two amino acids, that His 119 and His 1 or His 12, where do you think those are in the overall structure of the protein? No, these two residues are found in the active site. So these two residues are two of the amino acids that are capable of basically carrying out our chemistry. Now, there's another structure here that you need to kind of recognize as being different. And that other structure is our RNA molecule. Now, we've already talked about nucleic acids, and you've probably seen nucleic acids before, so it might be not too much of a stretch to kind of visualize like, oh, well, they have a phosphodiester backbone. But what I want you to notice is that everything that I'm drawing a circle around and that I'm about to remove the circle from, well, none of that is covalently bound to our enzyme. It's not covalently bound to the His 12 or His 119. Is there some sort of interaction going on with it? Yeah. Now, this dashed line right here and this dashed line right here, those are just to represent that this molecule kind of goes on beyond these two bases. Now, with that said, tell me, or actually, we'll go through it first. I want you to be thinking about what type of mechanism is this? Is this a general acid, general base, or a general acid or a general base, or is it concerted? Now, what I want to do is introduce you to each of the residues. Histidine 12. Notice how it is deprotonated. It has a lone pair of electrons, and what those lone pair of electrons are going to do is they're going to go and take this hydrogen from our RNA molecule. Now, what I think is most valuable when it comes to learning a catalytic mechanism for an enzyme is to identify any other amino acids that are involved. What are they doing in this same step? And in the step where histidine 12 is picking up a proton, well, look down here at histidine 119. The electrons that are shared between nitrogen and hydrogen, the nitrogen in the imidazole ring, and that hydrogen, where are they going? They're going back to our nitrogen. So essentially what that means is that that nitrogen is giving up that hydrogen. So his 12 is picking up a proton, and his 119 is donating a proton. Okay. So with all of that taking place, what's happening is our phosphodiester linkage is being broken. And if we go from this first cell to our second cell, well, between our first and second cells, our RNA molecule has been cleaved, and part of it has been released. In addition to that, notice how His 12 right here, at the moment in the second cell is protonated, and then His 119 down at the bottom is deprotonated. What is moving in to participate in our reaction beyond this would be water. Okay, so we've broken our bond, and now water is coming in. Now, what's water doing? Well, the water is donating a hydrogen or donating a proton to our nitrogen, and then this OH is going to our substrate. So water, by donating a proton right here, you could say that it's acting as an acid. Then If we look down at our third cell after our second step, what do we have? We have histidine 12 over here and 119 down here. Well, histidine 12 is deprotonated, exactly how it started, right up here. Same thing. Histidine 119 is now protonated, just like right here. Now, my question for you guys is when we look at histidine 12, and I'm going to go from this location right here to this location right here, and then to this location right here. Let's think about histidine 12's protonation state in each one of those spots. In the first spot, well, histidine 12 is deprotonated. In the second spot, histidine 12 is protonated. And then in the third spot, histidine 12 is deprotonated again. So it goes from deprotonated to protonated, back to deprotonated, so it can carry out the reaction again. Histidine 119 starts out protonated, is then deprotonated, then is protonated again. So it kind of goes in the opposite, or it follows like the opposite path that histidine 12 follows. So my question for you guys, is this general acid catalysis where an acid is donating a proton or an amino acid is donating a proton? Is this general base catalysis where an amino acid is accepting a proton? Or is this concerted acid-base catalysis where an amino acid is accepting a proton and then another amino acid is donating a proton? What do you think about that? Answer in the chat what you think that it is. Absolutely. It's our concerted. Sorry about the correction there. It's concerted acid-base catalysis because we have both. Histidine 12 is acting as a base, and then it acts as an acid, and then it acts as a base again. Histidine 119 acts as a acid, then a base, then an acid again. So great job, Milo. Thank you very much. All right. So now I'm going to go back a little bit and I'm going to share a video. I've got a video on my YouTube channel where I go through the RNase A mechanism. Um, Spend a little bit of time with it. It's really, I don't think that it's too complicated, especially when you isolate it down and you say, I'm going to look at histidine 12 and then histidine 119. Just look at individual residues. Now, there are only a handful of amino acids that are very important in acid-base chemistry, and those are amino acids that can be protonated or deprotonated. Now, ones that we've talked about, or that we haven't really talked about quite so much, serine and tyrosine. Well, serine and tyrosine, by virtue of them having alcohol groups, they can participate in acid-base catalysis. Are they the most likely? Not quite. But is it possible for them to? Yeah, absolutely. They can donate and accept protons. Now, think about this as your protonated form, protonated form versus deprotonated. Now, your protonated form is the form of the amino acid basically whenever you're below, when your pH is below the pKa. Your deprotonated form is whenever your pH is above your pKa. So, if you think about like a pKa value for aspartic acid or glutamic acid, that's going to be a fairly low pKa value. So at a neutral pH, so I'm going to say pKa about 4. I'll just give one round number for the both of them. At a neutral pH, so at a pH of 7, what are those residues more than likely going to be acting as? Well, more than likely, they're going to act as general bases. Now, one thing that's kind of complicated about pKa values and how they can vary a little bit is, well, in a long polypeptide, some group pKa values will change. So I bring that up just because Glutamic acid and aspartic acid, yeah, they can act as acids at a neutral pH. Um, will they? Yeah, they will. Is it super common? A little bit variable. But that's just where you have that kind of almost ambiguity in their pKa values and how they can change a little bit. Now, with that in mind, um, this is a graph that shows on our y-axis enzyme activity and on our x-axis pH. So our enzyme activity on the y-axis goes from basically 0 to infinity. I'm looking at this graph on the left-hand side, 0 to infinity. Well, I'll call that 100 maximum. And then on our x-axis, that's going to go from 1 to 14. So here what we have is at if something is acting as a base, well, it's going to be less active at a lower pH, at an acidic pH. So at an acidic pH, the GB, I'll say, general base, will be less active. And the opposite is true for an amino acid that acts as a general acid. Now, we also have kind of a bell-shaped curve that shows basically the range in which almost any enzyme involved in acid-base catalysis is going to act. It's going to have a particular range that it's going to be most active. Now, these ranges can change a little bit whenever you have different pKa values for different important residues. And this active form could be a very narrow region. Um, but I always like to think about this as bookends of the activity curve. You have an inactive form at a low pH, and then you have an inactive form at a very high pH. That's just because when you have different residues involved or multiple residues involved in the catalysis, well, they're going to run into a combination of protonation states that don't favor the reaction taking place. Okay, so that was acid-base catalysis. Any ionizable residue or protonatable residue, but include in that list tyrosine and serine. Now, for covalent catalysis, this is an important distinction between acid-base catalysis and covalent catalysis. In covalent catalysis, a covalent bond is transiently formed between the substrate and the enzyme or coenzyme. So think about covalent catalysis as, oh, we've got a covalent bond. Okay. Now, this reaction usually involves a nucleophilic group on the enzyme. That's an important distinction. Where is the nucleophile? It's on the enzyme. So the nucleophile is on the enzyme and the electrophile is on the substrate. Now, as an example to illustrate that, here what we have is an enzyme known as chymotrypsin. Chymotrypsin is from the class of enzymes known as proteases. And what proteases are is they are enzymes that basically clip up peptide bonds. So they break peptide bonds and, they break up proteins. Now, here what we have is an amino acid, serine 195. Remember, that was one of our ionizable groups, or one that could be involved in acid-base catalysis. And then right here, so here's our chymotrypsin with this, kind of amorphous shading. There's an amino acid represented by the single letter B. That's not a single letter code, but instead that single letter represents base. So there is a base. And what that base does is it abstracts or extracts, not sure what the right word is there. It's going to basically abscond, that's a good one. It's going to abscond with the proton from our serine. So what's that going to mean? Well, that would mean that serine would be deprotonated and therefore negatively charged. And therefore, as it's negatively charged, it's a really good nucleophile. So serine starts out as a pretty decent nucleophile because if you think about the alcohol group, that's got two lone pairs of electrons. And those little pairs of electrons are are looking for something. They're looking for a partial charge. So here is our polypeptide. Here's our peptide bond, N to C with the carbonyl oxygen and then our hydrogen. Well, the base in our chymotrypsin picks up this hydrogen. Our lone pairs of electrons go after that carbonyl carbon. And whenever that happens, we're going to bring a proton in that can, well, help break that bond altogether. And lo and behold, our serine and our carbonyl carbon form a covalent bond. So this is an example of a covalent bond being formed between our enzyme and our substrate. And this was done with the help of an amino acid on our enzyme acting as a strong nucleophile. Okay, so if we proceed from here, I think that it's good to look at, well, what are some of the different amino acids that are involved in this? But before we do that, I want to go ahead and jump forward to look at a mechanism for covalent catalysis. Oh, dang it. And that enzyme is known as lysozyme. Lysozyme is an enzyme that hydrolyzes peptidoglycan layer, or the peptidoglycan layer of bacterial cell walls by breaking beta 1,4 glycosidic linkages between N-acetylmuramate and N-acetylglucosamine, or NAM and NAG. Now, this right here is our polysaccharide. That's NAM, NAG, NAM, NAG, NAM, NAG. It's this on repeat and this is a word I like to use in perpetuity. It's a law word. My wife's a lawyer, so I heard it from her first. What we have is lysozyme acting on one of the bonds that connects NAM and NAG. Now, here is another model on the right-hand side of what that kind of looks like. There's a pattern that NAM, NAG, NAM, NAG, NAG, and so on. But what I want to draw your attention to is it doesn't just cut between, or it doesn't cut after every NAM. Instead, it's going to find basically the first NAG, and then it's going to find NAG, NAM, NAG, NAM, and after the second NAM, N-acetylmuramate, that is the bond that is going to be broken. So after second NAM, and you might think, well, how do I know which the second one is? Well, you can imagine that, or sorry, you would go to the very beginning of that polysaccharide. Now, this enzyme is also capable of kind of identifying, okay, well, here's my pattern, and here's the fourth one, and it's going to cut there. So, yes, this enzyme can pick up randomly within a chain, find 1, 2, 3, 4, and cut. Now, what I want to draw your attention to here is we've got a couple of amino acids that are highlighted as being important in the active site. Right here. Aspartate 52 and glutamic acid, or glutamate 35. Okay, so those are two amino acids that are pretty critical for the cleavage of this glycosidic linkage. But then I want to bring some other amino acids in. Aspartate 101, tryptophan 62, 63, alanine. Oh, what the heck? Alanine? 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 What? Tryptophan? Wait a minute. Wait a minute. These are non-polar residues. What are they doing? Those R groups are boring or kind of useless. I mean, no disrespect to them and their families, but they don't really, ugh. Well, here's the thing. Look right here. Carbonyl, carbon. Is that the R group for alanine? No, it's not. It's not the R group for alanine. Is that the carbonyl backbone? It is. Sure is. And then if we look further, we look closer, we enhance, we enhance. What do we see? The carbonyl oxygen has a dashed line next to a hydrogen. What is a dashed line from an oxygen to a hydrogen that's bound to a nitrogen? What does that usually indicate? I'm gonna drink my coffee while you guys come up with the answer. It's a hydrogen bond right there. Booyah. Milo, Adam, you're absolutely right. That is a hydrogen bond. So before we proceed, we previously talked about backbone hydrogen bonding. And when we talked about the backbone hydrogen bonding, what context were we talking about backbone hydrogen bonding? Sorry, take my sweatshirt off. We were talking about backbone hydrogen bonding from a structural perspective, secondary structure. And that kind of was like, oh yeah, we can form a alpha helix or a beta sheet. And that's fun. Great. We got some information there. But this shows right here that backbone hydrogen bonding can take place between the polypeptide backbone and your substrate. In addition to that, this also kind of reveals that, well, there are parts of the protein that are within the substrate binding site, different residues within the substrate binding site, that what they're doing is effectively holding that substrate in place. So they might not be there for the actual breaking of that glycosidic linkage. But I want to ask you, what if we were to take this alanine and mutate it? Now, alanine 107, alanine's a small amino acid. If we mutated that from an alanine to a, let's say, I'm going to go with a phenylalanine, PHE 107. My question for you is first, is the R group for alanine and phenylalanine, are they the same size? No. Do they have the same sorts of interactions? Not really. I mean, arguably, yeah, but in terms of their magnitude of their polarity, that's where I'm getting there, or their non-polarity. Phenylalanine is considerably more non-polar, considering that it has that bulky ring. So my question is, if we mutated this from an alanine to a phenylalanine, do you think that these atoms, well, a little bit more specifically, the carbonyl, carbon and oxygen, do you think that those atoms would be in the exact same location? They wouldn't, or it's, I would, I would put $5 down to say no, they wouldn't. Thanks, Darlene. Thanks, Milo. You're absolutely right. We're winning $5 each, all of us. I'm not sure who's going to take that bet, but we'll look somewhere on the internet for some prop bets about protein folding. So those atoms are going to be in different locations. And when those atoms are in different locations, is that substrate going to be bound or held basically the same way? No, it's not. I always kind of think about these amino acids up here and these down here. The ones that are in the substrate binding site. It's kind of like whenever you go to get a haircut and the person pulls your hair and then they do this, and maybe they'll hold your hair down here and then they'll cut here. Well, they're holding your hair in places separate from where they're cutting. They're positioning it right so that they can cut your hair properly. And that's what lysozyme is doing. And that's what all these amino acids in the top half of this and the bottom half of this are showing, independent of that aspartate and glutamate, glutamate, or glutamic acid. Okay. Now, with respect to the lysozyme, let's get down to business. Here is the lysozyme mechanism. And I like to start in the upper right-hand corner with the lysozyme mechanism, because then I can kind of get the lay of the land and I can see that, give myself an idea of what to expect. Glutamic acid 35. Is this glutamic acid or is it glutamate? Well, right here, it's glutamic acid because it's protonated. Down here, is this aspartic acid or is this aspartate? Well, it's aspartate. It's deprotonated. Okay. So that when I look at those residues, my first thought is, all right, there's probably going to be some movement of protons. One of them is going to donate a proton, one's going to accept a proton. Got it. That's what I'm going to think about here. That's my kind of inclination. Now, with that said, is that actually what happens? Because if something is capable of acting as a base, it's also a good nucleophile. So maybe, just maybe, and I know the answer is yes, that aspartate 52 is going to be the residue that establishes um, my bond with the substrate. Okay, so if we go over here, my substrate binds, and we've got our D and E here representative of ring D and ring E, so our fourth um, or our fourth ring in our polysaccharide. And what I notice is that my glutamic acid 35 donates a proton. It donates a proton. It acts as an acid. Acts as acid. Awesome. That's good to know. Whenever it donates that proton, well, then what that is going to lead to is the formation of an oxonium ion transition state. So this oxonium ion is produced after basically my, you know, the remainder of my polysaccharide has been released. Now, this is an instance where, well, we've got general acid catalysis that's taken place. Now, I said that this was going to be considered a covalent mechanism. It absolutely is. I think that when it comes to designating something as, oh, is this covalent catalysis or acid-base catalysis? I always kind of envision that it is when you have a covalent step that trumps that kind of is superseding over the general acid and general base or concerted acid-base catalysis. So we do have a step that is general acid catalysis. Now that oxonium ion, that positively charged carbon there, is able to establish our covalent bond with aspartate 52. So we have our covalent catalysis take place there. So at this point in time, in step number 3, so moving from this cell to this cell, we have our covalent bond between our substrate and our enzyme. Now, we want to get rid of that because we want our enzyme to be able to kind of regenerate and do the reaction again. And so what do we bring in? We bring in our old friend water. Water comes in, breaks that covalent bond. We have water acting as an acid and glutamic acid or glutamate acting as a base and picking up that proton from our water. That gets glutamic acid back to where it needs to be. And all of this gets aspartate back to where it needs to be, aspartic acid or aspartate 52. So water is a critical part of this enzyme regenerating itself. Now, what I want you to know about this is, and what's I think best to think about this is what are the steps that facilitate the covalent bond? What are the amino acids? Whenever it comes to understanding a mechanism, I think one of the most important things is looking at and isolating. And so isolating a single residue. So what I would recommend doing if you're looking at something like this is I would look at it like this. It's not the one that I wanted. I think you get the picture because I'm blocking everything out. All I am doing is I'm tracking my glutamic acid. What changes about glutamic acid? It's protonated, then it's deprotonated, then it's deprotonated, deprotonated, and then it's protonated again. So it starts protonated and I need to end it protonated. Isolating different components of it of any mechanism, I think is helpful because it gives you kind of a story in that amino acid's kind of myopic view. Okay, now we're going to jog back because we've talked about covalent catalysis. Now I'm going to bring up nucleophiles. Well, the nucleophilicity of a substance is related to its basicity. So there are a couple of different amino acids that can act as nucleophiles. Biologically important nucleophiles are negatively charged and contain unshared electron pairs. So one good example, or you know, something with a nitrogen or an oxygen or a sulfur is going to be a good, potentially a good nucleophile. So one thing that we've got is we've got two amino acids with sulfur. We've got methionine and cysteine. Which one's going to be a good nucleophile? Well, cysteine, because methionine has that methyl group. All right, top hat question. Oh, that's not an O. I knew this one was coming. I just like to kind of give you that. Okay, we got 45 seconds. I think we can get 20 people to answer it. 3, 6, done. Yeah, we're on our way. Yeah, 18. There's 20 seconds left. Yep. Yeah, we're gonna get it. Yep, 24, 25. I bet we can get 30. 28, 29, done. 30. I bet we can get 32. Yep, 33, done. Yeah, we got 33. Will methionine act as a good nucleophile? See our responses. Methionine will not. Cysteine can act as a good nucleophile. Methionine cannot. All right. Now, just as there's a nucleophile, we got to know about some electrophiles. Most often, when you see a electrophile, biologically important electrophiles are either positively charged or contain unfilled valence shells or contain an electropositive atom. So metal ion would be a good example of an electrophile. Alternatively, a carbocation, like what we saw in the oxonium ion in the previous mechanism. Now, our third type of mechanism, so we've talked about acid-base catalysis, covalent catalysis. Now we're on to metal ion catalysis. Well, nearly 1/3 of all known enzymes require the presence of metals for catalytic activity. Metalloenzymes contain tightly bound, so metalloenzymes bind their metals super tightly. Metal-bound cofactors like iron, divalent or trivalent, copper, zinc, manganese, or cobalt. By contrast, there are metal-activated enzymes. These only loosely bind to metal ions, and the ions are usually sodium, Na+, potassium, magnesium, or calcium. So cofactor is typically going to be a metal ion. A coenzyme is generally an organic molecule. Now, enzymes have a tendency to go between two different states, an apo form and a halo form. The apo form of an enzyme is the inactive form. So that prefix is added to the name. So if you were to see apohexokinase, that'll be the inactive form of hexokinase. Halohexokinase would be the active form. Now I'm just using that as a term that's a familiar enzyme for us, but that's a terminology that you might see. Okay, so we've talked about ribonuclease A. Now what we're going to look at is an example of a metal ion catalyzed reaction. So carbonic anhydrase, this is an enzyme that we've talked about previously. Carbon dioxide reacts with H2O to produce HCO3 and a proton. How does this work? Why does this work? Well, one thing that I want to draw your attention to is 1, 2, 3 histidines. These histidine residues are within the active site. Now, do you think that those histidine residues, so okay, let's think about this. These histidine residues have basically, they've kind of ganged up on in some respects, and they've kind of surrounded a zinc ion, a zinc 2 plus. Add to the chat. Do you think that these histidines are protonated or deprotonated when they have that zinc in place? I like it. I like it. I like it. You're absolutely right. They're deprotonated. Okay. So you could think about that as this is going to happen in a slightly, at very least, a neutral pH, because the pKa of histidine is about 6.1. So, a neutral, maybe a slightly above neutral pH is where this is going to take place. Now, what's happening here? And we're starting in the upper left-hand corner. So I'm going to actually kind of draw some boxes over all this stuff. Um, those zinc ions are coordinated with this histidine. And after that, that zinc ion that's kind of trapped there by those histidine residues, that zinc ion is going to attract a lone pair of electrons on a water molecule. So it's going to bring an H2O down, and it's going to kind of hold that in place. Now, when you think about a water molecule, um, does anyone remember what the pKa of water is? I'll give you a little bit of a hint. Starts with a 1 and ends with a 4. Absolutely. That's our Ka. Perfect, Milo. But our pKa is about 14. And so if you translate that pKa of water to a solution, so let's say that you put water in a or solution with a pH of 11. That water molecule is going to hold on to both of those hydrogens, no problem. Um, if the pKa of water, however, were to change, then that water molecule might give up a proton. Okay, that sounds a little bit crazy, but that's exactly what happens here. What zinc is able to do is the zinc holding on to the single water molecule causes the pKa of that singular water molecule to drop from 14 down to 7. So now that water molecule in a neutral pH, so I'm going to call it, I'm going to go with neutral plus, pH of 7.1. That water molecule, if its pKa is now 7, well, then it very well might donate a proton. It'll look like this. And that's all because zinc kind of altered water and made it give up a proton. Now, that sounds like it bullied it. I didn't really intend for it to sound that way, but that's effectively what happens. So zinc causes water's pKa value to drop, causing the likelihood that water is going to donate a proton to go up. And whenever it donates that proton, well, the lone pairs of electrons on that oxygen can then be used to kind of corral over or lasso in a carbon on a CO2 molecule. And whenever it does that, electrons that are found within the double bond between carbon and oxygen go towards this oxygen. And those lone pairs of electrons also are attracted to our zinc ion. And we get this crazy looking structure right here, which can then be displaced by another water molecule. So our HCO3 can be released. So why is this happening? Well, it all goes down to the metal ion, the zinc ion, can cause water's pKa to drop whenever water is present. That leads to an increase in the concentration of hydroxide at the active site, which enables that hydroxide to kind of corral in a CO2 molecule. This is an example of metal ion catalysis. Now, you might be thinking, well, it sounds like this is a little bit like covalent catalysis. It does sound that way. I think that you are right because it does have a nucleophile, or histidine residues, does have an electrophile. But what makes this different from covalent catalysis is that we never have a covalent bond formed between our enzyme and our substrate. We have basically a metallic bond between our oxygen and our zinc, but we don't have any sort of covalent bond formed between our substrate, either the water or the CO2, and our enzyme. Because the histidine, it's almost like there's a buffer that exists, or kind of a barrier that exists between the histidines and the substrates. Okay. So we've talked about three different mechanisms. We've talked about carbonic anhydrase, lysozyme, and RNase A. I want you to think about those as metal ion catalysis, covalent catalysis, and acid-base catalysis. Now, they are certainly not trivial, but they are good for you to kind of get a footing on. Now, we've got another question here. This is going back to our lysozyme mechanism. So actually, I'm going to jump back and look at this again for a second. So the question is about glutamic acid 35. Now, look at it and think about its kind of life cycle. How does it start? How does it end? Well, it's protonated, then it's deprotonated, then it's protonated again. Now let's go look at our question. Our question is, what is glutamic acid or GLU35 doing in the upper left cell of the lysozyme mechanism? Okay, it's acting as an acid, a base, not acting as an acid or a base. I think we can get 30 answers. Yeah, I'm going to be very, what's the word? Bullish. We did it. 30. Great job. 33. Wonderful work, everyone. 24 out of 33 answered correct. It is acting as an acid because remember, it's protonated and then it donates that proton. And, I did not include the reference, but you had the PowerPoint. You could look back at that if you wanted to. But it is acting as an acid. Okay. Next up, I just want to introduce these a little bit. Proteases. Proteases are a class of enzymes that cut proteins. They cut peptide bonds. Now, they need to have a dipeptide, so they need to have two amino acids in order to cut it. Now, proteases, they're classified, not like secret, but they can be classified into different groups. Serine proteases are a family of proteolytic enzymes that have an active site serine. Oh man. What amino acid do you think is present in a aspartic protease's active site? That's right, an aspartic acid. I just love the creativity sometimes. It's not a creativity. It's pragmatism. So serine proteases, two examples are chymotrypsin and subtilisin. Thrombin is also a important protease that's involved in blood clotting. Um, Trypsin, chymotrypsin, and elastase are digestive enzymes. Subtilisin is a bacterial protease. If you ever know of anyone who has a stroke, does anyone know what the drug that's administered early on in stroke patients? Add it to the chat. The three-letter identifier will work. It's TPA or tissue plasminogen activator. So that's a drug that activates a protease. Now, plasmin is also a serine protease that breaks down fibrin polymers of blood clots. And here we go. Tissue plasminogen activator, or TPA, cleaves the proenzyme plasminogen to yield plasmin. Now I'm going to stop right here to give you guys like a cliffhanger of sorts. This is the end of season 1 of the TV show Lost. Okay, with that said, we're going to continue with this stuff on Monday. I hope you have a wonderful day. Thank you very much for coming to class. I hope you have a wonderful weekend, and I will see you guys later. I'm going to stop my recording. Thanks, everyone. You did a great job. Bye.